This is a problem that will explain the universal law of gravitation. And the universal law of gravitation is an equation that works for all points in our universe related to gravity. So the equation is capital G, which is a constant, m1, m2 over r squared. Capital G, like you said, is the constant, and that value is 6.67 times 10 to the negative 11. And then the unit for that is Newton meter squared per kilogram squared. That's the constant. M1 and M2 separately are masses that are involved, and R is the distance between them. So we're going to find the net force on the moon from the sun and from Earth. So the mass of the moon is 7.35 times 10 to the 22nd kilograms. And that 10 to the 22nd is important. The mass of the Earth is 5.98, times 10 to the 24th kilograms. And the mass of the Sun, which is much bigger, is 1.99 times 10 to the 30th kilograms. Okay, so we're going to do two separate equations on this. All right, so the Earth distance from Earth to Moon, distance from Moon to the Earth, is something that we don't really know off the top of our heads. 3.84 times 10 to the 8th meters. And the distance from the Sun to the Earth, which then by association is to the Moon, is 1.5 times 10 to the 11th meters. It's a much farther distance. Okay, so the first thing we want to figure out is the force of gravity on the moon from the Earth. Okay, so you can subscript that any way you want. So we can assume that the force of gravity between the Earth and the moon and the sun and the moon is going to be different. Okay, now which one is going to be bigger depends on the size. So think about what's important. On the top of the equation, you have the constant, which is going to be the same for everything. And then you have two masses. So if you have two big masses, you're liable to have a big force. Now, if your radius is much bigger, then you're going to have a smaller force. Now, if you have something that's big on the top and big on the bottom, it's effectively going to cancel out in terms of magnitude, and you're going to end up with something of a similar size. So if we look at this and plug in, we have 6.67, and I'm going to drop the times 10 to the and put it in terms of E. So times E, negative 11. All right, and then that's going to be multiplied by M1, which is going to be the moon. So 7.35 times 10 to the 22nd, which is going to be multiplied by M2, which is the Earth. So it's 5.98 times 10 to the 24th. And that's going to be divided by the radius from moon to Earth. 3.84 times 10 to the 8th. And that is squared. So what we have is a whole bunch of big numbers on the top and a relatively large number on the bottom. So when we resolve all of this into a final answer, we're going to get a force of gravity of 1.99 times 10 to the 20th newtons. It's pretty large. Now we do the same thing for the next problem, which is to find the force of gravity of the sun on the moon. Alright, same thing, we have our constant, 6.67 times 10 to the negative 11, and that's going to be multiplied by the mass of the moon, which was 7.35 times 10 to the 22nd, multiplied by the mass of the sun, 1.99 times 10 to the 30th, is E30, and that is going to be divided by the distance, 1.5 times 10 to the 11th squared. Okay, now this one, if you compare the two, up here we have times 10 to the 22nd, and then we have 10 to the 24th. On the bottom we have 22nd and 30. Okay, so this is going to increase by a couple orders of magnitude. But then on the bottom of the top one, we have times 10 to the 8th versus times 10 to the 11th on the other one. So in terms of that, we have big numbers on the top and the bottom, but they're ultimately going to resolve themselves and become two things of very similar magnitudes. So we're going to end up getting a force of gravity from the sun on the moon of 4.34 times 10 to the 20th newtons. So not much bigger. Now, depending on how these things acted, they can both be acting at the same time, which they're going to be. Now, visually, in terms of a diagram, what you have is the Earth here with the moon around it, and then the sun over here. All right. Now, in terms of forces, the force of gravity of the Earth on the moon is pulling it this way. It's going to be towards it at all points. So technically at this location it'll be like this. But it's always, when it orbits around, going to pull towards the Earth. Now the sun's force is going to be going this way. So these two things can be combined using trigonometry. We don't have to do it right now, but it's good to know that the sun and the Earth collectively put together end up increasing the amount of force felt on the moon. Right, so there are all your values, which there are a lot, and this is using the universal law of gravitation, which involves plugging in numbers and solving. Now from here, what we could do is find the linear speed of the moon, which we're going to very quickly. So the formula that we would use, because the moon is attracted to the Earth, it's going to be Fg equals force centripetal, which is mv squared over radius. So the force of gravity of the moon on Earth is 1.99 times 10 to the 20th, and that's going to be equal to the mass of the moon, which is 7.35 times 10 to the 22nd, multiplied by the velocity squared, divided by the radius, which is the distance between the two, of 3.84 times 10 to the 8th. All right, we're going to solve this by multiplying both sides by the radius. So we do 1.99 times 10 to the 20th, and multiply that by 3.84 times 10 to the 8th. We're going to divide by the mass of the moon, which is 7.35 times 10 to the 22nd, and then take the square root. So we're going to get an orbital speed of the moon of 1,019.6 meters per second, which is pretty fast. So that means we have a speed of 1 kilometer per second. And then we could find the orbital period of time. So we could say, how long does it take for this to go around? So we know that the moon is going to orbit us in a certain amount of time. It's going to be a month, just about. All right, so let's figure out what that actually is. How do we find it? Now, what we want to do is find period. So we need an equation that has capital T. And since we know the radius, we could say that velocity is circumference divided by period, because knowing the radius is going to tell us the circumference. So we can rearrange to solve. So we're going to get period is equal to circumference divided by velocity. So that's going to be 2 pi times radius, 3.84 times 10 to the 8th. That's going to be divided by the velocity, 1,019.6. So we're going to get an orbital period, and we plug this in, of 2 pi times 3.84 to the 8th divided by 1,019. And we're going to get a really big number, 2367755.798 seconds. All right. Now, what we want to do is convert that to a more manageable value. Now, there are 24 hours in a day, and there are 3,600 seconds in a day. So that means one day, which you might know this, one day is 86,400 seconds. So we could take this number and divide it by this number to get how many days. So 2367755.798 divided by 86400 is going to give us 27.4 days, which we know already is pretty close to what the actual orbital period of the moon around the Earth is.